Today's lesson is on section 7.2, solving linear systems by substitution. In this chapter so far, we've worked on one method of solving a linear system, and that first one is graphing. And if you are taking notes along with me, I'd like to start by writing this stuff in the red down. I'm going to teach you our second method for solving a linear system today, which again is substitution. Graphing, I believe, is the best one to start off with first. If you're first learning to solve linear systems, graphing is the one to go with because it gives you the nice visual of what's really happening when you're solving a linear system. We're taking two equations, and the nice visual of the graphs of those two equations shows us what we're looking for. That one point where those two lines cross. The intersection of the two lines, that's the point. That's the solution to both those systems, or to that system. Solution to both equations, but the solution to your system. So graphing gives you that nice visual. I think that's a great thing for students to be able to see first. Then when we go into other methods like substitution, or like the one we'll go into next, which is elimination, then at least students know what they're really looking for. They can have a picture in their mind. Even if they're not graphing it, they can still picture, here's what's happening. I'm finding the solutions of all these equations, but there's a way to find that one number, that one solution that works for both equations in my system. So again, I'm going to talk about substitution today. What do we need to know about substitution? Well, again, that's our new method. Here's a few quick bullet points I want you to copy down about it. Sometimes it's a little faster. It's something where, again, we're not graphing, so we don't necessarily have to make scales for our graph or make a big grid and graph two lines. So sometimes it can be a little faster in that regard that I don't have to make the picture of what's happening. It is more algebraic. Again, in this case, now we're moving variables around. I'm plugging numbers in for variables. I'm manipulating an equation. So more algebra going on rather than the visual, the more geometric graphing. And again, there is no visual, though. You don't get that picture like you do when you do a graph. But since we started off with graphing, at least students can still think of what's really going on when we're finding the solution using substitution. So here's an example of what happens when we use substitution to solve a system. And substitution actually isn't something new to us. Students have dealt with problems where they substitute values in before for a variable. Here, for my example problem, I'll kind of use this and show what I mean. So I have two equations, y equals 3x plus 2, and x plus 2y equals 11. Students have done other things in the past where they've substituted like a number in for a variable. So for example, over here, this isn't part of the problem, but something to think about. We've had situations where sometimes they tell us, well, we know that y equals 5 in this problem, so then evaluate it or solve the equation knowing that y is 5. And so what have students done in the past? Let's say we're working with this bottom equation, the second one. So if I know that y equals 5 in this problem, well, then what we do is we substitute the value 5 in for the variable y, and then I could either solve that equation or if again, if it was an expression, I could evaluate it and find my answer. So we have done things like substitution. We've done substitution before. We've just usually only substituted one value in for a variable. But now, I'm going to cover that up again, not really part of our problem, but something to think about. Now, when we have a system of equations, we're going to do something similar. We're going to substitute something in for a variable in one of the other equations. Because remember, in a system, we're saying that both these x values, whatever they are for our solution, has to be the same. And our y values also need to be the same thing. So in a system, these are equal. Okay, the y's are equal and the x's are equal. Well, knowing that, again, think about our example. I'll bring it back here, where our number equals y equals 5. Okay, in that case, since y was equal to the number 5, I could substitute 5 in for y in this equation, and then continue from there, whatever I needed to do. Well, look at this equation I have in the system. This one says y equals, but instead of 5, it's just an expression which will stand for some number. Instead of 5, I just have this whole expression, x plus 3x plus 2. So not just a number by itself, but some terms, but it still says y is equal to these things. So in a system, here's what we do to substitute. Just like in the past where I could substitute just this 5 in for y, well, in a system, I can take, if I have y is equal to, and then this stuff on the other side of my equation, that expression, I can substitute all of that in for y. And this is again, we're substituting something in. So something we've done in the past, just not with an expression like this. I'm going to substitute 3x plus 2 in for the y in that second equation. So what's it going to look like now when I rewrite it? Well, the second equation will look like this. I still have the x plus, and I still have the 2, but now in parentheses, I'm going to have this expression instead, because this stuff is equal to y is what the system's saying. 3x plus 2. That equals 11. So there's my second equation rewritten, but now I've substituted 3x plus 2, that expression, in for y. This is called substitution. This is how we do it. Now what can I do from this point? Now it's just like solving a multi-step equation. I've got to get the x by itself on one side, and it's a linear equation. So I know how to do all these steps. So I'm going to distribute 2 to both these things. So when I multiply 2 times each of the things in parentheses, again distributing, I'm going to get x plus, well now I'll get 6x plus 4 equals 11. Again, just like solving a multi-step equation, now I just kind of keep going. I can collect like terms right here. X plus 6x gives me 7x. Plus 4 equals 11. Subtract 4 from both sides. I'm kind of running in my grid here, but that's okay. I'll get 7x equals 7. And divide both sides by 7. I get x equals 1. So again, what I found right now is x equals 1. Now picture back, though, and students should remember, when we did graphing, what did we find? What kind of solutions are we looking for? We're looking for an ordered pair. So we're looking for a point like an x and a y, correct? So what I found right now is just my x-coordinate. I found that the x-coordinate for where these two lines cross is 1. If I want to find the y-coordinate, well, how can I do that? And usually I'll ask students, and they can kind of come to the agreement and figure out that if I want to find the y-coordinate then for this point, well, I can just plug it into one of these equations, because we're saying that this ordered pair, whatever it is, my solution, it works for both equations, right? It's the one point where the two lines cross. So that means I can plug one in here and solve that for y, or one in here and solve that for y. In either case, I should get the correct y value, the correct y coordinate for my ordered pair that I'm looking for. So I'm going to plug it into the top one because that one looks a little easier in this case. 3 times 1 gives me 3, and if I add 2, I would get y equals 5. So this ordered pair, the point where the two lines cross, would be 1, 5. Just in case you don't believe me, I'm going to show you that too on this grid down here. So I'm going to bring these equations with me. Bring these down here. Again, I found that the solution, I think, using substitution, using that method, was 1, 5. Well, if I use the other method, graphing, I should still get the same answer, correct? So right now I'm going to graph this equation, y equals 3x plus 2. My y-intercept of that equation is 2. The slope is up 3 over 1, up 3 over 1. If I reverse direction, I can make a few more points just to make sure I make a nice line here. But this one would look something like this. Then I'm going to graph the other one. We'll say in green here, x plus 2y equals 11. This one I could change it around to slope-intercept form, but it is actually set up nice for intercepts method as well, even though one of them will be a decimal number, but that's okay. If I put in 0 for x, 11 divided by 2 gives me 5.5. So I get 5.5 for my y-intercept. And if I put in 0 for y, x equals 11, so my x-intercept is 11. So I'd go all the way over here. 11, 0 would be somewhere off the grid, just a little bit though, right over there. And 5.5 would be right about here, at about 5, up 5.5 more. And so here would be this line. And again, I didn't graph it perfectly. But if I had a ruler, I'd probably be a lot straighter. But you get the idea. So where's my two lines crossing? It looks like there's a point right here that they're crossing at. And what do you know? That point is 1, 5, which is exactly what I found using the other method. Same thing I found when I was graphing. Same thing I find is when I'm substituting, using substitution. So is either method really better than the other one? No. Again, sometimes one is faster, one's a little more visual, but it doesn't matter. I want us to be able to use both of these methods. So here's what substitution looks like. Here's what graphing looks like is what we did right now. Here's what substitution looks like. We should be able to use both of these methods to solve a linear system. I'll go through another example here just to show us one more time what it should look like if I'm solving a system using substitution. So again, I've got a system of equations here, 3x minus 5y equals 11, and x equals 4y minus 8. This second equation right here is set up good for substitution because it's solved for one of the variables. I have x equals, and then this stuff, 4y minus 8. Well, again, in a system, the variables should stand for the same thing. So in this case, if x equals 4y minus 8, well then in the other equation, I can plug that expression in, that stuff in, and that's called substitution. I really should say I'm substituting those things in for x in the first equation, and I should be able to solve that equation and find out what y is. So I'm going to plug, since it says x equals this stuff, I'm going to plug that stuff in for x. This is using substitution. So now 3 instead of x, I'm going to put what that expression is, 4y minus 8 minus 5y equals 11. So I've just rewritten that first equation, but I've substituted in the second equation, set equal for x, and substitute that expression in for where x goes in the equation. Now I can just keep solving like a multi-step equation. 3 times each of the things in parentheses there, so 3 times 4y gives me 12y, 3 times 8 gives me 24, minus 5y equals 11. Once I get to this step, I can collect like terms, 5y and negative 5y, or subtract 5y, sorry, 12y, and subtract 5y. That should give me 7y. Minus 24 equals 11. And then I'm going to add 24 to both sides. And I'm going to get 7y equals 35. Divide both sides by 7. Y equals 5. So again, that looks like my answer, but I'm not totally done with this problem. Okay, all I found is the y-coordinate. I found the y-coordinate for that point where these two lines would cross. That's going to be 5. If I want to find the x-coordinate, I got to plug it back in to one of the equations and see what I get. And again, it should not matter which equation you plug it into. I'll tell you right now, it will not. If I plug it into the top one, if I take 5 times 5, that would give me 25. So I'd have 3x minus 25 equals 11. If I add 25 to both sides, I get 3x equals 36. And divide both sides by 3, I get x equals 12. So that one's telling me that the x-coordinate should be 12. Okay, I'm going to write that in. If I try it in the other equation, plug 5 in for y in the second equation. 4 times 5 gives me 20. 20 minus 8, what do you know? That also gives me 12. So again, just showing you, it wouldn't matter which equation you plug it back into. Either one will still give you the same answer because that's the solution to our system. I'm going to show us one more example. I'm not going to go all the way through this example. I'm just going to show us how to get it started because there's one more trick that we need to know maybe before we do some of the problems in the assignment today or before we practice it. Again, substitution is a very good method. Definitely works to solve our system. We don't have to make any graphs or anything. But one other thing you need to do if you're going to use substitution is you need one of these equations to be set up for substitution. And what I mean by that is we need one of those equations solved for a variable. One of these equations has to be like x equals and then stuff on the other side, or y equals and all the stuff on the other side, some expression. If it's not like that, I can't use substitution. Then substitution does not work. So right now, as I'll present this problem to the class also, we'll look at this one, this linear system, and say, okay, which of these equations could I solve for one of the variables? And really, the answer is either one. Either one I could solve for x or y and make that equation work. Which one would be a little easier, though, I think is the top one. Because in this one, I only have to do one step, and then I can get that equation solved for x on the top one. Since it says x minus 2y equals negative 6, if I just add 2y to both sides, that will get x by itself on the left side of the equation. So now, rewriting this one over here, what do I have? I'll have x equals, and I'm going to write it like this, 2y minus 6. Now I've got that equation solved for a variable. It's solved for x. So just one more note to notice when we're using substitution, you do need to have one of the equations solved for a variable. If it's not, then I can't use substitution yet. So this system, the way it was originally, the way I had it on the board, okay, just like this, you can't use substitution yet. It does not work. But once I change it, once I added 2y to both sides and got x plus equals 2y minus 6, now I could use this with the bottom equation. I'm going to use this one and this one together and use substitution. X equals this expression, 2y minus 6. So over here in this problem, I can substitute that expression in for x, I could get 4 times in parentheses 2y minus 6 plus 6y equals 4. And now, like the previous problems, I can just keep distributing, collecting like terms, and I can solve and find my solution. So just note substitution, a great method. With this last example, just showing you that you do have to get it set up for substitution occasionally in some problems.